Hi. I make no guarantees about not delaying things further, but I'll do my best. So I'm Richard Reeve. I'm based in the University of Glasgow. I'm jointly funded by the university and by the Purbright Institute. I decided not to give a talk this year because I didn't feel I had anything particularly new to say from what I've talked about at previous EuFMD and GFRA meetings, but Vilna cunningly persuaded me to talk about what I hadn't done yet as a kind of excuse for why I should talk. So I'm going to have a little go at that, but mostly I'm going to talk about stuff that we collectively have already done, both in the foot and mouth world and elsewhere. But vaccine modelling covers so many things that there are lots of things I'm not going to talk about in 18 minutes. In particular, I'm not going to talk about what happens in disease-free countries where vaccination is, there's a lot of political issues associated with vaccination, and it's a hugely complicated one, and reasonable people disagree on what the right policy is. I'm also not going to talk about whether vaccination policies have worked, and an awful lot of modelling goes into understanding how in post-vaccination monitoring and things like that about how vaccination has worked in practice and whether different schemes for vaccination would work. I'm really going to stick what I didn't actually realise was the theme of this particular session on vaccine efficacy. So that's very lucky. And I'm going to talk about vaccine modelling that investigates vaccine efficacy and vaccine selection, vaccine match. So without more ado, so what do we actually want vaccines to do? Or what do vaccines do, in fact? I mean, they increase protection against infection or against disease. At the herd level, they reduce individual exposure to disease because there are fewer infected individuals. And at a meta-population level, they reduce herd exposure to FMDV because fewer farms are getting infected, and so there's less infection pressure on an individual herd. So how do we work out whether a vaccine works? Well, we know this back from 1908, really, and we're still doing exactly the same thing today. We're doing live animal challenge trials, I mean, this was a sufficiently clear idea that it's developed independently in different fields, and it's now standardized, and many of us are reasonably happy with the PD50 test, where we take 5 animals and give them a full dose of vaccine, 5 animals, give them a quarter of a dose of vaccine, and 5 animals and give them a 16th of a dose of vaccine, and we see how many animals were protected. And really, that's all there is to it, this Spearman-Kerber test that's been around for a long time. Obviously, in South America, they use a different test of protection against podal generalization we heard about earlier on, where they just give 16 animals a full dose. And that turns out to be a better way of finding out whether or not 75% of your animals are going to be protected, but it gives you slightly less information about how strong your vaccine is. So depending on what you want to do, you can set up different experiments and set different thresholds on them, and you can do something like this ROC curve here to look at the sensitivity and specificity of all of these different challenge tests that you might set up if you had 15 animals that you wanted to challenge. And indeed, you can show that that experiment will produce this sensitivity and specificity here in the cross. And in fact, you can achieve that level of sensitivity and specificity with different experiments, which involve fewer animals. But to be honest, the savings in animals is probably more than outweighed by the increase in legislation to prove that works. So more importantly, people think about predicting efficacy now serologically, because the animal challenge work is hugely expensive and there are lots of ethical issues associated with it. So we try to build models that predict protection from VNT and ELISA data, or one or the other, or both. And again, we can show that we're very good at predicting that an animal will be protected, and we're very good at predicting that an animal won't be protected. And that all sounds like really good news until you drill into the data and you realize that actually the animals that we're identifying as not being protected were all the controls. And all of the low titers because of what we suspect is a feature of just how good the vaccines are that we're testing, because most of the live animal challenge trials are being done on high-potency vaccines manufactured under strict conditions, even animals with very low titers turn out to be protected in these trials. And so the animals that aren't protected, and there are some, are balanced by animals with very similar with identical titers that are protected, even though those titers are incredibly low. And so it's quite difficult to get around the fact that these assays aren't telling us directly about protection. There are 50% of the animals that get this titer are going to be protected, and 50 aren't, even though they're really low. And when we look at what happens here, so we can just extrapolate the models and say, well, what protection would I expect for a titer way below the minimum sensitivity of the test? And it turns out that when we do that, we say that animals that have absolutely no titers against FMDV, we predict will be 30% protected for some vaccines, which is clearly wrong. And this is data from a whole series of vaccine trials that we assembled, but it's not just me who comes up with this. So this is from Krista Klerk's lab, and we're looking at here these curves that many people have seen before. We see that we have a dose-response relationship here. Well, dose-response, a titer response relationship where low titers we're predicting won't be protective. But for many of these are all different labs doing the same VNT here. We see that at a log titer of 0, which is a titer of 1, we predict 70% protection in this lab. I mean, we just know that has to be wrong. So we have big problems with having assays that correctly characterize protection at these low levels. At a population level, we can do quite well, and that's often enough. But one of the issues is just that if we need to connect this stuff to real challenge data and see what's happening. We can't just look at titers and say, okay, well, 75% of the time that's protective, because we'll start making mistakes like this that makes us think that animals that are completely naive to foot and mouth disease will be protected in practice. One of the problems, and it's not far from the only one, is that these tests are very variable. And loads of people have observed before that ELISA tests are more reproducible than VNTs. But from our data, it's very clear that VNTs are more predictive of protection. Nonetheless, we'd like VNTs to be more reproducible. And so we have a PhD student in Pirbright, Jamalia Sanawi, who's basically working on picking apart the test and trying to work out exactly what features of the test are causing the variability. Maybe there's really nothing we can do about it, but maybe there are some things that we can do about this and understand why we're getting well failures that are positive and well failures that are negative, and what exactly is going on here that's making the VNT more variable than the ELISA. So when we put all this together, we can build a model of serological protection. We can build a model of protection, of clinical protection from just the serology. And here what we've done is we've taken a series of 10 PD50 trials that were done on an Omanissa vaccine by Krista Klerk's lab, and we've looked at we've taken the first PD50 test as our training data, and we've used the other 9 tests as trial data. And these results in the kind of blocky, sorry, it's not very pretty. The blocks here are, this blue line here at 9 PD50 is actually the efficacy of the vaccine itself. And these blocks here show the variability in the challenge trials of what variability you actually get from the challenge trials when you're looking at how protected the animals really were in a live challenge experiment. And the red curves are what we predict the efficacy would be from the serology. after training it with one vaccine. And on average, we end up with a nice smooth curve here. And we see that the serology is actually predicting protection better than the challenge trials. With only 15 animals, we can predict protection better with serology once it's been suitably trained on data for that specific vaccine. And obviously, that's the lesson learnt from South America, where they have extremely effective mechanisms for determining batch acceptance from serology. So something coming back to something else that we don't really, well, at least I feel I don't understand, is subclinical infection. So these vaccines sometimes they're not as protective as we might like, and so this is an example from a partially immune herd that Jose Gonzalez was working on in South America, and in blue we can see how many animals were clinically infected. Which is around the 20% mark across here, and then in red is how many seroconverted, and that's more like that's between 40 and 90% that we're seeing were determined to have been infected, even though they didn't have clinical disease, and in this case, I mean, this seems to be a result of the fact that the herds were partially immune, and we see exactly the same thing from vaccination, that is. We see exactly the same thing, though, in Tanzania, from one of our PhD students who's been working there, who found that only 10 to 20% of the animals were getting infected in an FMD outbreak, and this was in herds where no vaccination was practiced. We don't know the serological, we don't know the history of these animals, but most of them were very young, and so we don't think. Certainly, these are 4 separate outbreaks that we monitored them through, and we don't believe that they had been exposed to all 4 of these viruses. They've probably been exposed to at most one. But when we look at the titers again, we find that 65%, 90%, 73%, and 70% of them were infected. So there's something going on that's causing subclinical infection that's not causing disease. And that would obviously just be a matter of academic interest if it weren't for the fact that when people look at what happens when you in other diseases, here we're looking at E. coli 157, what happens in other diseases when you manage to reduce clinical disease so that you end up, in this case we're looking at super shedders that are being reduced to kind of normal shedding levels for E. coli. What happens at a metapopulation level when you reduce that super shedding, when you reduce the clinical disease in this case, then they see massive effects at for very low impacts. You get superlinear effects that really help you out when you're trying to control the disease. And how would we get this subclinical result? Well, again, Jose was talking about this 2 years ago, that there's a nice dose-response relationship with both clinical disease and infection, and if you can get your animals to be exposed to less virus, then they're very likely to become subclinically infected. And so if you can come up with some mechanism for doing that, you can aid the process of controlling the disease in areas where it's completely endemic and you're not going to be able to just stamp out or control it through infection. So I think there's something very interesting going on here, that we've got a whole series of disconnected bits of information that we want to put together on how subclinical infection may be able to help us in controlling the disease in endemic areas where we have no immediate expectation of being able to eliminate the disease completely. And just to point out, this really does work. Here we've got some data from epidemics where this is a retrospective analysis of the 2001 foot and mouth outbreak, where in the UK, where they've been trying to calculate the within herd R0 for foot and mouth disease, and their estimates in these different herds vary from about 10 to 80. As the within herd R0, and giving you a situation where in 2 generations of the disease you've covered the entire herd. Whereas in Jose's paper, where he was looking at at what the effective reproduction ratio was with all of these subclinical cases, you've got R naughts of about 2 within the herd. So there's a completely startling reduction in R naught that's coming about from something. Obviously, it's partially, vaccine protection, but there's definitely something going on. If you can get R naught down from 50 to 2, then that's quite promising, I would have thought. And when and for people who might think that there's an issue that these subclinically infected animals wouldn't be protected in the future, there's at least some evidence that that's not the case. There's a paper that came out this year that when you look at this was a transmission experiment in Pirbright, that one animal in this transmission experiment had clinical disease, and it does have higher titers, but the other 3 got seroconverted, but they didn't show clinical disease. But these titers here are titers, just going back to this this graph of Tom Willems, they're about 1.7 to 2 log titers, and these are titers that are protective. And so there's some possibility that these animals are going to be protected in the future. So I know I'm running on a bit, so I'm going to skip through this second bit, because that was the main bit I wanted to talk about. I think there's a lot of work that we can do to try to refine what's going on in the vaccine efficacy itself. In terms of vaccine selection, I don't have a huge amount more to say than I've said in the past. I mean, obviously, the gold standard here is, again, cross-protection challenge trials. But people use R1 values to measure them because it's utterly impractical to use cross-protection challenge trials on a large scale. And something that I've been working on for a long time, and collaborators in Pirbright and on Destaport, is sequence-based prediction to skip to learn from the serology to do this work. So this is some work from Bernd Hass's group showing essentially that the R1 values aren't giving you a good indication. It's stuff that everybody knows, that we have very high PD50s for most of these vaccines. They're going to be very good even for emergency vaccination, but the PD50s are all very low. And so there's yet more to understand there about what's going on. And our serological predictors, our sequence-based predictors, do pretty much as well as serology here. The grey bars are how correctly vaccine choice is being made for some SAT2 and SAT1 strains, and the black bars are the sequence-based predictors choosing them. And you can see that by and large we do as well, with one exception here. We do as well or better than the serological predictors. And we can then do some antigenic characterization of the viruses doing this, and this is a phylogeny with some coloring giving you antigenic phenotype. And we can do reverse genetics and demonstrate these are actually the causative substitutions that are affecting at least the serological changes, if not protection. And then one more thing that I think we need to add into this story is this is some work by Marta Lusko and Michael Lessig on flu, looking at predicting the clade survivorship of flu strains. And now we're working with them to incorporate, this was purely sequence-based in the past, and now we're working with them to incorporate serological data into that, and we're now predicting the future survivorship of strains that feeds into the vaccine selection meetings for the seasonal flu strains. And at the moment, it's very early days. I wouldn't like to promise that this will be the right, this clade is the one that's going to survive, but we're making predictions about which vaccine strains are going to be best in this area in the future. And this South Africa is, we believe is the best strain to choose for the Southern Hemisphere next winter. And we can do this by combining the serological information we have from large-scale sequence data coming off all of the surveillance platforms they have for flu. So, I mean, overall, what gaps do I think there are? I mean, essentially, I think we don't understand enough about the serological assays themselves, both the ones we currently use, the ones we should be using, and the ones we haven't developed yet. And that's especially in the sense of cross-protection. We really need to understand more about what's going on there. I personally think that understanding the importance of subclinical infection is going to be really handy down the road. I'm not quite sure whether that fits into the vaccine efficacy quite as much as it should, but I think that's a really interesting thing that I'd really like to look at. And I think this study of looking at factors that affect viral clade survival and their implications for vaccine choice has real promise. And to do all of this, we need more sequence data, more samples, especially from Africa. So there were loads of people involved in all of this work, because I've talked about thousands of people's work here. And yeah, thank you very much.
Thanks very much, Richard. I think that actually followed on very nicely from Aldo's talk earlier in the first session. And actually, I would have had one question for you, which you sort of perhaps answered at the end, which was really what is the link between subclinical infection and vaccine efficacy, and whether you were suggesting that maybe looking at generalization to the feet would not be necessarily the best readout for these tests.
Well, I mean, I guess my interest is essentially in a situation where we don't think the vaccines are going to be very good, and we don't think we're going to be able to control the disease in the short term. Can we do something that what do you get from protection from disease rather than protection from infection? Do you get something useful out of that? And if so, is it enough to justify using it? If that makes sense. I should mention that the EuFMD have been Anna Ludi and others were talking about vaccine matching a couple of weeks ago, and there's a vaccine performance, more field-based talk in November. So if people are interested in that kind of stuff, because there's obviously a lot more to be said.
Okay, well, thank you very much again, Richard. So I think we better move on in the interest of time, and we now